So next, let's talk about something called implicit functions. So implicit functions is something that you cannot explicitly write y equals to something, right? So for explicit function, so we have a dependent variable y, and we have an expression, or we have a function of x. So we can write the function as y equals to fx, right? So we can write a y on the left-hand side, and on the right-hand side of the equation, it's only about x, right? So there's no y in the right-hand side. So in this way, we say that we can have an explicit function of y equals to something, where y is a function of fx. So for example, y equals to 3 times x to the 4th. So on the left-hand side is y and only y, right, the dependent variable. And for the right-hand side is a function that's related to x, the independent variable. So the dependent variable and independent variables on different sides of the equation. Okay. So for implicit function, we use an expression to to denote that. So the expression is the big F, which is expression about y and x, and this thing equals to 0. So for example, if we move the 3x to the 4th to the left-hand side, so we have y minus 3 times x to the 4th equals to 0. So in this equation here, the independent variable, which is x, and the dependent variable, which is y, are on the same side of the equation. So in this way, we say that this is an implicit function, right? So here in this example, f(y)(x), the big F, equals to y minus 3x to the 4th. So this is expression. Okay. So all the explicit function can always be transformed into the expression here, or all the explicit function can be transformed into implicit function, right? So for example, if we want to transform the explicit function y equals to 3x to the 4th to the implicit one, so we can simply move the 3x to the 4th to the left-hand side, right? So this is y minus 3x to the 4th, which is 0. And so this is a big F. So for any explicit function, because we can always find the expression of y equals to something, right? So the left-hand side is only y, and the right-hand side is a function. So we can move the fx to the left-hand side. So this becomes y minus fx equals to 0. So this becomes an implicit function. So we can always find the implicit form of the explicit function. But the reverse is not always possible, right? So think about an example here. So f(y)(x), the expression, what if something like this? E to the, oh no, you haven't learned that. So think about another way. So y cubed times x squared, then plus y, a square root of y, times x to the 8th, or something like that, right? So in this equation here, so this thing equals to 0, right? So for example, we have a very complicated expression involving x and y here, and y is the dependent variable, and x is the independent variable. Right? Suppose we have a very complicated form like this. So in this way, it's very hard for you to substitute out the y, right? I mean, it's very difficult for you to write something like y equals to any form of x, right? Because y and x are all together all the time, right? It's difficult to exclude y or to write y solely on the left-hand side, like this form, right? So in this way, the reverse is not always possible because sometimes it's hard for you to find out the expression of I equals to fx very easily. And for other forms, so for example, look at this expression here. Right? So this example shows that sometimes sometimes y is not even a function of x. So you cannot write y equals to something. Okay, so for example, so big F yx equals to x squared plus y squared minus 4 equals to 0. So if you have learned the function of a square, the function of a circle, so you will know that this is exactly a function of a circle, right? So for example, if the relationship between x and y can be written as x squared plus y squared equals to a squared, where a is a constant. So we say that this is a function of a circle. And if we draw that in the plane as a center at 0, 0, right? And there's a, and there's a, minus a, and the minus a, right? Okay, so we have a 4 here. So the coordinate here is 2, and then 2 minus 2 and 2 minus 2. Anyway, so even if you don't know what it is, if you draw this expression, right, x squared plus y squared minus 4 equals to 0. If you plot this into the plane, you will find that it's actually a circle. So based on the definition of a function, we know that y is actually not a function of x, right? Because for any given x, there are two y. Right? So x does not uniquely determine y. So y is not a function of x, right? So this relation is called expression. The big F yx here is called the expression of y and x. It's not a function of y and x. Where y is not a function and y cannot be written as y equals to fx, right? But even if there's no explicit form, remember that this is called explicit form of a function. It's not explicit form, but it can have an implicit function like this, right? The implicit function is just an expression, but y doesn't have to be a function of x. So this is called implicit functions. And sometimes we want to find out the derivatives of the implicit functions. And we'll know how to, right, in the following. So there's something called implicit function rule. And we need to derive this, right? We need to talk about that for the rest of the time. And to tell you how to find the derivatives of the implicit functions. Okay, so before we derive the implicit function rule, there are 3 facts that need to be satisfied, right? The 3 basic facts. So first, very easy to understand, if 2 expressions, so here we use expressions, not functions, to denote, right, the relationship between x and y. So the expressions means the big F, right, y and x. So we call this expression, right, or a equation involving y and x. So if 2 expressions are identically equal, So that means f1 equals to f2. So both f1 and f2 are expressions that involving y and x, right? So if the two expressions are identically equal, that means that they are exactly the same, right? f1 is just f2. So for example, f1 may be y plus x, right? And f2 equals to x plus y, right? So the expressions are identically equal. And if this is the case, then their respective total differentials must be equal, right? That's easy to understand, right? Because they're just the same thing. So the differentials have to be the same thing also. And the second fact, differentiation of an expression that involves y, x1 to xm. So y is the dependent variable, and the x1 to xm are independent variable. So here we have an expression that involves one dependent variable and m independent variables. So differentiation of the expression involving this will yield an expression involving the differentials dy and then dx1 to dxm. So that means that, for example, if f y x1 to xm, right? Because we have m independent variables here. For example, so the expression may be y squared plus x1 squared plus xm squared, right? So suppose we have expression that looks like this. So the differentiation of this expression will contain the differentials of all the variables from dy to dx1 and dxm, right? So it cannot only have dy, dx1, and then dxm minus 1, right? Because we have m variables here, m independent variables here. So differentiation has to involve all the variables in the expression. So there has to be expression of dxm in the differential form of the expression, right? So that means that for all the variables that contained in the expression, in the differential forms, there have to be the differential form of all the same kind of variables, right? You can now miss some of them. So the third fact, the differential of y, which is dy, right? dy is a differential of y. It can be substituted out. So the fact that we can now solve for y does not matter, right? So after you take the differentials, you get dy, dx1, and all the way to dxm, right, in the equation. So the third fact means that you can always substitute out the dy. That means that you can always write dy equals to a function of from dx1 to dxm, right? You can always write dy solely on the left-hand side after you take the differential of the expression, right? So these are the three facts about the implicit function. So given all the facts, consider we have an expression like this. The big F, which is the expression of y and x1 to xm. So we have m independent variables, and y is the thing we're interested in, right? So y is the dependent variable. So that thing equals to 0, right? Because this is a standard way we write the implicit form of a function, Right? Remember that when we talk about the implicit function, the expression is like this. So big F of y and x equals to 0. So that means that we can always find the implicit form that equals to 0. Right? So for example, y minus this thing equals to 0. Right? So suppose we have a function, an expression, big F, which is an expression that contains all these kind of variables, equals to 0. And because this thing equals to 0, which is a constant, so it means that when we take the differentials, it should also equals to 0. Right? So the differential, the df, equals to d0. Right? We just take the differential of the left-hand side and then the right-hand side. So df equals to 0, d0, which is 0, right? Which is 0. So if you write the total differentials of the big F expression, so it looks like this. Yeah, it's like this. So Fy means the partial differential of the big F with respect to y, and then times dy, and then plus F1, which is the partial differential of the big F with respect to x1, right? And then Fm means the partial differential of the big F with respect to xm. Right, so the summation of all those terms equals to 0. Right, so we just talked about that before in the last chapter, in the previous videos. And so suppose we have explicit function that y equals to a function f, the small f, from x1 to xm. Right, suppose we can find the explicit form of the function y equals to the little f. So the function has a total differential. If we write the differential of this function, it should be dy, the total differential of y, equals to f1 dx1. So here, this is a small f1. So that means that the partial derivative of the small f, the explicit function that we don't know, right? We don't know the explicit function form, that we can assume there is an explicit function form. So f1 is the partial little f, the function, with respect to x1. And f2 is a partial differential of the small f function with respect to x2. Right? So this equation is the total differential form of dy, if we know the explicit function form. So we can substitute this equation into here, right? So we can change the dy using the right-hand side of this thing. And then we can combine the common terms. So we can find the equation here. We combine these two equations and find this thing, okay? So this thing means the fy times f1 plus f1. This is a small f, this is a big F, and then times dxy, and the plus the similar terms, and the summation of all the similar terms equals to 0. And notice that all the dxi, I mean from dx1 to dxm, all the dxi can vary independently from one another. So this means that dx1 can be positive or negative, and dx2 can be positive and negative, and dxm can be positive or negative. Right, so all of the dxi's, they can change independently from each other. Right, they don't have to. So dx1 and dx2 are not related. They're independent from each other. So it can be positive or negative, or simply 0, right? So you cannot control the numbers here. You cannot control the dx1, dx2, dxn. They can be any number. So if you want to let the summation of all the terms to be 0, the only way to do this is to let the coefficient terms, all the coefficient terms, to be 0, right? Because dx1 to dxn means the little bit change of dx1 to dxn. So they cannot be 0, right? They can be anything. So that means that fy times little fi plus big fi equals to 0, right? Since all the coefficient here are 0. And the coefficient can be written as big fy, since it's a common term for all the terms here, times the little fi, which is the partial derivative of the small f with respect to xi, and then plus big fi, which is the partial derivative of the big F with respect to xi, right? And this thing equals to 0 for all the terms, for all the I. So we can have the implicit function rule, because what we are interested is the fi, right? So little f is the explicit function, right? So y equals to little f from x1 to xn, right? So what we are interested is to take the derivative of y with respect to xi, any of the x here, right? So this is just fi. So fi is defined to be partial y over partial xi, right? So this is what we want to find. It's because we don't have the explicit form, right? The only thing that we know is an implicit expression, big F. But we're interested in the derivative of y with respect to the independent variables, so which is fi, right? So here we can write fi as minus big fi over big fy, right? So from here we know this, right? We just use the fi from the left-hand side and we move the big fi and then divide it by fy. Right? So this is this expression. So that means that if we want to know the partial derivative of y with respect to any of the xi, but all the things that we know is the implicit expression, big F. So we can use this kind of function to find out the partial derivative, okay? So for example, if we only have one variable, x, one independent variable, so the implicit expression is big F yx equals to 0. So we can use the equation and we find that the dy over dx, so here fi is just to take the derivative of y with respect to x, right? Since there's only one x, so we don't have any partial derivative here, right? Because we only have one variable, right? So the derivative of y with respect to x is just the total derivative. It's not partial derivative, right? Because there's no other variable other than this x. So the partial derivative is downgraded to, it's degenerated to dy over dx, right? Since we don't have any other variables. So this is just equal to the big F, partial big F over partial x, divided by the big F, partial big F over partial y, right? So did this thing. So for example, find the derivative of the implicit function, this thing. So because we have only one independent variable, x, so the partial derivative is downgraded to the total differentials, right? So we don't have partial differential, just a total differential. So dy over dx equals to this thing, right? So it's a minus sign here. And then fx is, so this is a big F, right? Big F is this thing. The partial derivative of the big F with respect to x, so which is minus 12 times x cubed over big Fy, which is the partial differential of big F with respect to y, which is just 1, right? So this is 12 times x cubed. And then, again, find dy over dx for the expression, which is x squared plus y squared minus 4, right? Which is the circle we've seen before. So we know that y is not a function of x, but it doesn't mean that we cannot find the derivatives here, right? We can use the implicit function rule to find out the partial derivative, which is the derivative here, or the total derivative here. So dy over dx, again, the thing, equals to, pay attention that there's a minus sign here. So fx equals to 2x, right? Just a partial derivative of big F with respect to x. And then fy is just 2y, so this becomes this thing, right? So even if y is not a function of x, but we can still find the derivative of y over x using the implicit function rule. And the third case, we need to find the partial y over partial x for f equals to this thing. So here we have two variables, x and w, right? So when we take the derivative of y with respect to x, it's called a partial derivative because we have to consider w as a constant, right? Okay. So again, we can use a function, the formula before, which is this, right? And then there's a minus sign. So fx is to take the derivative of f with respect to x and to assume that y and w are constants, right? So this should be the thing. And then to take the derivative of y, we assume x and w are constants. So it's this thing. So we can easily find the partial derivative using the formula there. So this is how we find the derivative of y with respect to any kind of x, which is an independent variable in the implicit function form, right? So even if y is not a function of x, we can still find the derivative using this way.